Ever wondered why water from your faucet flows the way it does, or how airplanes manage to fly? Welcome to the intriguing world of fluid dynamics, an essential branch of physics that helps us understand such phenomena. It's a field that explores how fluids, both gases and liquids, behave under various conditions. It's what makes your morning shower possible, powers hydroelectric dams, and allows birds and planes to glide gracefully through the air. Today, we're going to delve deeper into this fascinating subject, focusing on two fundamental principles: the continuity equation and Bernoulli's equation. These equations are the cornerstone of fluid mechanics, providing essential insight into the behavior of fluids in motion. They're the keys that unlock our understanding of why and how fluids move the way they do. So let's dive into the fluid world and unravel two fundamental concepts: the continuity equation and Bernoulli's equation. Picture a flowing river or water from your tap. The continuity equation is a fundamental principle in fluid dynamics that states that, for an incompressible fluid substance, the flow rate of mass remains constant along a pipe or any flow. Imagine you're holding a hose and you squeeze the end of it. What happens? The water speeds up, right? This is the continuity equation in action. The volume of fluid entering a pipe, or hose in this case, must be equal to the volume of fluid exiting it. Now, let's dive a little deeper. Mathematically, this principle is expressed as A1V1 equals A2V2, where A represents the cross-sectional area and V represents the fluid velocity. To put it simply, if the area of the pipe decreases, the velocity of the fluid must increase to maintain the same flow rate. This is why the water in our hose example speeds up when we squeeze the end. The area has decreased, so the velocity increases to compensate. This equation can be applied in a variety of scenarios, from understanding how blood flows in our veins to predicting how rivers will behave. So, the continuity equation gives us a window into the relationship between area and velocity in a fluid system. It tells us that if the area changes, the velocity must change in the opposite direction to keep the mass flow rate constant. In essence, the continuity equation is a conservation law, stating that mass is conserved in a fluid flow. It's a fundamental concept in fluid dynamics that helps us predict and understand how fluids behave in different situations. And this is just the tip of the iceberg. With the continuity equation and other principles in fluid dynamics, we can delve even deeper into the fascinating world of fluid behavior. Stay tuned as we uncover more fluid dynamics principles in the upcoming scenes. This equation shows the relationship between area and velocity at different points in a fluid system. Now let's move on to Bernoulli's equation. Named after Swiss scientist Daniel Bernoulli, this equation is a powerful tool for understanding the relationship between pressure, velocity, and potential energy in a fluid substance. Bernoulli's equation is expressed as P plus 1/2 rho V squared plus rho GH equals constant, where P represents pressure, rho is the fluid density, V is the fluid velocity, G is the acceleration due to gravity, and H is the height above a reference point. These variables capture the essential characteristics of fluid flow: pressure, kinetic energy, and potential energy. But what does it all mean? Essentially, this equation tells us that the sum of pressure, kinetic energy per unit volume, and potential energy per unit volume remains constant in an ideal fluid that's in steady, inviscid flow. In simpler terms, if you increase the speed of the fluid, the pressure decreases. And if the fluid rises to a location where it has more potential energy, its kinetic energy and pressure will decrease. This interplay, this dance of energy transformation, lies at the heart of many everyday phenomena. Let's delve into some applications to see how Bernoulli's equation is versatile. Take, for instance, the lift on an airplane wing. When air flows over the curved top surface of the wing, it travels faster than the air flowing under the wing. According to Bernoulli's equation, the pressure on top of the wing decreases, creating a pressure difference that lifts the airplane. Or consider blood flow in arteries. When an artery narrows, the blood's speed increases and the pressure decreases. This principle is crucial for designing medical devices and understanding cardiovascular health. Even the charming behavior of fountains can be explained with Bernoulli's equation. As water is pushed through a narrow nozzle, its speed increases and the pressure decreases. This allows the water to shoot up into the air, creating a beautiful display. Each example showcases the interchange of pressure, velocity, and potential energy in a fluid system. It's this interchange, this balancing act, that Bernoulli's equation so elegantly captures. Bernoulli's equation is a cornerstone in fluid dynamics. It's a mathematical reflection of the physical world around us, a testament to the power of scientific inquiry. It's an equation that helps us understand the world, predict outcomes, and engineer solutions. So every time you watch a bird glide effortlessly in the sky, or marvel at the human circulatory system, or simply enjoy a fountain's display, remember Bernoulli's equation. Remember the interplay of energy, the dance of forces that makes these phenomena possible. And as we navigate the world of fluid dynamics further, let's keep this energy dance in mind. Because ultimately, understanding fluid mechanics is about understanding the energy transformations that drive the world around us. Stay tuned as we continue to explore the fascinating world of fluid dynamics. We'll connect the dots, tie together the principles, and see the big picture in the next scene. But for now, let's appreciate Bernoulli's equation in all its mathematical elegance and practical utility. Now, let's connect the dots. The continuity equation ensures the constant flow rate of mass, while Bernoulli's equation sheds light on how pressure, velocity, and potential energy interact within a fluid system. These two equations, though seemingly different, are intrinsically linked in the world of fluid dynamics. The continuity equation, with its simple assertion of mass conservation, is a cornerstone in understanding fluid flow. It tells us that in an uncompressible fluid, the mass flow rate remains constant along a streamline, a fundamental principle that shapes our understanding of fluid behavior. On the other hand, Bernoulli's equation, named after the Swiss mathematician Daniel Bernoulli, provides a powerful tool for understanding the relationship between pressure, velocity, and potential energy in a fluid. This equation beautifully illustrates how these factors change in a predictable manner along a fluid flow, providing insight into fluid behavior. Now, let's take a moment to appreciate the real-world applications of these equations. The continuity equation has massive implications in engineering fields such as hydrology and aeronautics. It helps engineers design efficient and safe water supply systems, and it's also fundamental in understanding how air flows over an airplane wing, a key aspect in aeronautics design. Bernoulli's equation, meanwhile, has a wide range of uses. It explains the lift on an airplane wing, the flow of blood in arteries, and even the behavior of fountains. It is a keystone in fluid dynamics, and understanding it can open doors to numerous scientific and engineering fields. So, what's the takeaway? These equations, while complex, provide a gateway to understanding the intricate world of fluid dynamics. They illustrate how different factors interplay within a fluid system, providing a framework for predicting and understanding fluid behavior. Whether you're a student exploring fluid mechanics or simply fascinated by the wonders of liquids and gases, these equations open the door to understanding the dynamic nature of fluids. If you enjoyed this journey into fluid dynamics, don't forget to like, subscribe, and share your thoughts in the comments below. We've dived deep into the world of fluid mechanics today, unraveled the mysteries of the continuity and Bernoulli's equations, and glimpsed the science that powers the fluid world around us. These principles are not just theoretical musings, they're the driving forces behind the natural and man-made phenomena we see every day. From the flow of rivers to the flight of airplanes, from the siphoning of petrol to the functioning of our very own circulatory system, these equations hold the key to understanding the fluid dynamics at play. It's a vast and fascinating field, one that's full of surprises and wonders waiting to be discovered. So don't stop here. Keep exploring, keep questioning, keep diving deeper. There's so much more to learn, so many more connections to make, so many more secrets to unravel. And remember, every question you ask, every concept you grapple with, every moment of curiosity brings you one step closer to understanding the complex, beautiful world we live in. So never stop asking, never stop learning. Here at, we're committed to fueling your curiosity and helping you make sense of the world around you. We've got more exciting journeys lined up for you, delving into different branches of physics, exploring more equations, theories, and principles. So if you're not already part of our community, hit that subscribe button and join us. And if you have any questions or suggestions, or if there's a particular topic you'd like us to cover in future videos, feel free to drop a comment below. We'd love to hear from you. Until next time, keep exploring the fluid wonders of our world. This is signing off.